Okay, to recap what we talked about in the last lecture, which was Wednesday, we looked at the stabilities of the different cycloalkanes. And what we saw was that cyclopropane was the cyclic alkane that is least stable because of the mismatch between the 60-degree bond angle and the 109.5 degree sp3 hybrid orbital angles. And so cyclopropane can actually be fairly easily opened up with hydrogen gas. Cyclobutane was a little bit better because the 90-degree bond angle is getting closer to the 109.5 sp3 hybridized orbital. Cyclopentane we would have predicted to probably be the most stable because the 105.5 degree or 105 degree angle is very close to 109.5. And when we get to cyclohexane, what we see is if we have all of the carbon atoms flat, we've got a 120 degree bond angle. And so now I'm going in the opposite direction of my 109 degree sp3 hybrid orbitals, and so we would have sort of a mismatch between the hybridization orbitals angles and the angles in the cycloalkanes. So remember, for cyclopropane, the idea here was that 109.5 degree sp3 hybrid orbitals can't adopt a 60-degree bond angle. So what happens is, instead of the orbitals overlapping head to head, they overlap sort of askew, and so therefore we have a carbon-carbon bond that's not very stable. This is what we would call strain energy in the molecule. So 90 degrees is getting a little better. 105.5 is even better than that. But what we saw was that for the cyclobutane and the cyclopentane, that we had the ability of the molecules, or of the cycloalkanes, to actually pucker, so that they could form a non-cyclic or a non-linear or non-planar structure. And this was really true for cyclopentane because one of its conformations is what's called the envelope form. And so this basically allows the carbons to adopt their 109.5 degree ideal sp3 bond angles, but it also allows to eliminate some of the eclipsing interactions that you might see from two hydrogens that are on adjacent carbons. If the alkane ring was perfectly flat, those hydrogens would be perfectly eclipsed, and so some of the puckering allows the hydrogens to actually then adopt not a true gauche conformation, but certainly not being completely eclipsed. So when we went to cyclohexane, what we saw was that one of the conformations that cyclohexane can adopt is what we're going to call today the chair conformation. And in the chair conformation, all of the carbons then can adopt their sp3 hybridization. So they all will have 109.5 degree bond angles. And so that's perfect. If all the carbon atoms were in the same plane, we'd have a 120 degree bond angle, and we'd have the orbitals kind of not head-to-head overlap, but at a skew. And the other thing that the chair allows us to do that we'll see in a few minutes is that it allows us to eliminate any eclipsing interactions between hydrogens on adjacent carbons. And what we'll see here is we'll see that the hydrogens are actually perfectly gouged to one another. Now this is just one of the conformations of the cyclohexane, and we'll talk about a couple of these, but this is what's commonly referred to as the chair conformation. So let's just talk a little bit about the chair conformations and the positions of basically groups or hydrogens in the chair. So if you look at the chair conformation, you have positions that are above the plane of the ring and positions that are below the plane of the ring. Now, if I was to write out sort of the flat version of cyclohexane, like this, those positions are pretty clear. Now, this is, again, what I called last time the Hallworth representation. That structure should probably be more realistically written with hydrogens kind of like this. But the idea here is that you can clearly see the positions that are above the plane of the ring and the positions that are below the plane of the ring. And so we're going to have cis-trans isomerism possible in the cyclohexanes because we can have a group above the ring and a group below the ring to be trans, or we can have a group above the ring and another group above the ring to be cis. And we still cannot interconvert cis and trans unless we open up the cyclohexane ring with basically by breaking the bond open. So looking at this cyclohexane chair conformation, and it's called a chair because I'll draw this out in a minute, but this is kind of the carbon skeleton of the cyclohexane, and so it kind of looks like a chair. It actually looks more like one of those beach chairs. But the idea here is that 4 of the carbon atoms are in a plane. One carbon sort of puckers up, and the other carbon sort of goes below the plane to generate the chair. And we'll talk about what's called the boat conformation, where the 2 carbons actually are both in the same direction. So they both go kind of above that plane generated by these 4 carbons. So in the chair conformation, we're going to have 6 positions above the plane of the ring and 6 positions below the plane of the ring. So let's go ahead and identify those first. You can clearly see that these 3 hydrogens lie above the plane of the ring. And these 3 hydrogens down here clearly lie below the plane of the ring. Now these other positions are a little bit more difficult when we begin to see that whether they're above or below, but it's actually easy to tell because each carbon has to have one position above the plane, one position below the plane. So if we identify that this carbon, for instance, has a position below the plane, then that means this hydrogen is above. So I'll use triangles for the positions, well, for the position above the plane of the ring in this case. So this position over here with this carbon, if this one is above the plane of the ring, then this carbon is below the plane of the ring. So why don't I just do it this way? So call it A for above and B for below. So here was a below, here's a position above and below. Over here, this position was below, that means this position is above. On the back carbon, this position was clearly above the plane of the ring, that one's below. This one was below, then the other position is above. And over here, this position was above, and so that position is below. So we've got 6 hydrogens above the plane of the ring and 6 positions below the plane of the ring. And what I've done is color code those in this slide to show you the blue hydrogens are above the plane of the ring and the yellow hydrogens are below the plane of the ring. Okay, so that kind of gives you a little bit of a feel for the positions above and the positions below. And this is going to be important when we try and draw the cis and trans isomers of the substituted cyclohexane rings. Now notice that there are 2 types of positions on the chair cyclohexane ring. There's actually positions that are represented here by these yellow or orange rectangles. These are positions that are roughly perpendicular to the plane of the ring. And so these positions are what we're going to call axial positions. Positions that are where the hydrogens or the groups are roughly perpendicular to the ring. So there are 3 axial positions above the plane of the ring and then 3 axial positions below the plane of the ring. For The other positions then, these are roughly in the plane of the ring. And so we call these positions equatorial positions. And so equatorial positions are roughly in the plane of the ring. And there are 6 of those. And every carbon in the chair conformation has an axial and an equatorial position. And the axials are easy to spot. The equatorials are actually probably easy to spot as well. Okay. Now, if we combine this diagram with what's above and below the plane, you can see that as we go around the ring, we have, let's start here, an axial position up. Then the next position above the plane of the ring is equatorial. The next position in this carbon behind the ring is axial. The next one is equatorial that's above. The one over here, axial up, equatorial up. So the axial and the equatorial positions alternate as we go around the ring, being above the plane of the ring. Now, these ball and stick diagrams that I have here are nice, but how are we going to draw the chair conformation of cyclohexane? And so this takes a little bit of practice, but what we do is we draw 2. Well, let's draw another one. That was not a very good try. Let's draw a position now. We'll draw 2 lines that are roughly parallel to each other. And then we draw sort of a V shape here and a V shape there. Okay. And so that's going to be our 6 carbons in the cyclohexane chain. Let me whip one out here really quick that's a little bit better. There's a little bit better one. So then what we do is we draw in our axial positions. Now, the idea here is to draw the carbons so that the positions are roughly tetrahedral. So I've got a position up, above, and above. There's my 3 axial positions up. Here are my 3 axial positions below the plane of the ring. Then equatorial positions go out in positions that are roughly parallel to the ring. Okay, and so this is how we're going to draw chair cyclohexanes, and then we're going to place groups on here, and ultimately at the end of this we're going to learn how to evaluate the different energies of those conformations. So just to show you what this looks like in a little bit cleaner diagram, here are your equatorial positions that lie roughly planar or roughly parallel to the ring. And then here are the purple ones are the axial positions that are pointed above or below the plane of the ring, and they're perpendicular to them. And then if we put those 2 together, we can see in the pink we have axials, and then in the blues we have the equatorials. So this is a much better diagram of the chair cyclohexane than what I had drawn just a few minutes ago, but we'll get plenty of practice on drawing these. So we have axial positions and equatorial positions, and half of the axial positions are above the plane of the ring, half of the axial positions are below the plane of the ring, and therefore the other half of the equatorial positions lie below or above the plane of the ring. Okay, so let's talk about the conformations that are possible for a cyclohexane ring. Well, one of the types of conformations that we can have, or processes, is what's called ring flipping. Okay, and ring flipping doesn't mean that I take the ring and I just rotate it. What ring flipping means is I'm going to actually draw the other conformation of that cyclohexane ring where my axial and my equatorial positions actually become reversed. So if we have our chair cyclohexane here, let's say I grab this carbon with my hand. Okay, so there's my hand. It's not a very good one, but it's good enough. And I'm going to grab this carbon and I'm going to move it up here. If I do that, I'm going to end up now with both carbons above the plane that was generated by the 4 planar carbons. Well, this conformation, which we could sketch something like this, that's called the boat conformation of cyclohexane. Should probably really be called the canoe conformation, because that's what it looks like. But it turns out that the boat conformation of cyclohexane is the least stable of all the possible conformations. And there's 2 reasons for that. The first reason is because these 2 hydrogens, which I sometimes call the flagpole hydrogens, those are going to be really close in space, and so they're going to interact with each other. The other reason is that when you look at these sets of hydrogens, you can actually see that they are perfectly eclipsed to one another. Whereas over here, and we'll see a little better view of this in a minute, this hydrogen is actually gouged to those 2. So looking down this carbon-carbon bond, you have a staggered conformation, whereas if I was over here, and such a little person for such a big hand in the last slide, looking at down this carbon-carbon bond, I would actually see the eclipsed conformation. So those are the 2 reasons why the boat conformation is the least stable, is because the hydrogens are now eclipsed and the flagpole positions are actually there's steric hindrance between the 2. And you can see that a little bit cleaner here. If you look at the space filling diagram, you can definitely see those 2 hydrogens close in space. Okay, so this is actually the first half of a ring flip, is to grab the hydrogen and move it up and form the boat. The other half of the ring flip is to move the bottom carbon down. So let's just take a look here at the boat conformation. So if I have my huge eyeball here looking down the plane of these 4 carbons, what I would see is I would actually see here's my 2 CH2 groups, and then here are my hydrogens. Those are definitely eclipsed in the boat conformation. Okay, in the final movement then of the ring flip, I'm going to go to the other carbon and I'm going to grab it and I'm going to move that carbon down. And so when I move it down, that's going to complete the ring flip. And so now I'm going to have what I consider to be sort of the left-hand version of the chair. If you're a left-hand person, then you can call this the right-hand version. But we have these 2 sort of mirror image versions. Drawing this one, I would draw it sort of like this. That would be my chair for this conformation. But the key thing with this, with doing this ring flip, is that for the most part, there's enough energy at room temperature to accomplish this ring flip. So rings are constantly flipping from one to the other. There are ways to stop the ring flip, and maybe we'll get into those next. Maybe we'll get into those here at the end. But the idea is ring flips can occur. These are different conformations, because all I did was rotate around a single bond, several single bonds. But notice what happened in this molecule. And I'll do it here. So this carbon right here that I'm going to call carbon 1 is down here, this carbon, number 1. Now notice that the axial position here in the equatorial position here in blue and the axial position here in pink, after the ring flip, what happened? What happened was my equatorial position now becomes axial and my axial position now becomes equatorial. So when you do a ring flip, all of the positions interchange. Axial becomes equatorial, equatorial becomes axial, and on and on and on. But notice what didn't change. What didn't change is that this equatorial position lied above the plane of the ring. This axial was below the plane of the ring, and after the ring flip, it's still above and it's still below. So the pink and the blue being above and below, or being axial and equatorial in this case, what changes is whether the position is axial or equatorial, but not whether it's above or below the plane of the ring. Okay. So that's what happens in a ring flip, and so that allows us to write different conformations for the chair cyclohexanes. So here is another example. In this case, I'm looking at carbon 4. This carbon after the ring flip would be this carbon. And so I have the purple hydrogen here that's axial and above the plane of the ring. After the ring flip, it's equatorial, but still above the plane of the ring. Over here, the hydrogen is below and equatorial. Down here, it's axial, but still below. So for cyclohexane molecules then, the barrier of this ring flip is about 11 kilocalories per mole. Basically, the barrier is going through the boat conformation. So if you go from this to the boat to the final ring flip, if you plotted this as energy, where energy increases, you would actually have a diagram that looks like this. And so you would have what we called in general chemistry an activation energy. And so that activation energy would be about 11 kilocalories per mole. At room temperature, you have about 20 kilocalories per mole of kinetic energy available to the molecule. So cyclohexane molecules are constantly ring flipping back and forth. And as long as the group doesn't, and as long as these groups don't become too large, then they'll still ring flip at room temperature. Okay. So that was just cyclohexane. Cyclohexane is pretty boring. Let's add an alkyl group to cyclohexane. So let's say we add a methyl group. Well, that methyl group of 1-methyl cyclohexane, that methyl group could either go in the axial position or it could go in the equatorial position. And how would I interconvert these? Through the ring flip. Now, the question is, I now have two different conformations. One where the methyl group is axial, one where the methyl group is equatorial. And the question is, which one of these two conformations is more stable? And the next question is why? Okay. So as a general rule, the most stable conformation of a substituted cyclohexane is the one where the largest alkyl group is equatorial, or the largest alkyl groups are equatorial. So this is the rule, but that would basically tell us that this conformation is more stable, and this conformation with the methyl group axial would be less stable. Why? Because it's not necessarily intuitively obvious as to why having the methyl group equatorial would be more stable than having it axial. Well, what we have to do is we have to look at a model of this and see that, like we looked at with the alkanes, the non-cyclic alkanes, when you look at those, what we found was that it was easier to say, okay, there are so many destabilizing interactions in this conformation versus the other one that makes this conformation less stable than this one. So in a lot of cases, it's easier to look at the destabilizing interactions as opposed to stabilizing ones, because the stabilizing ones they're not as important as the destabilizing ones. Let's just put it that way. So what's a destabilizing interaction for this conformation? Well, if we look at the methyl group being axial, it undergoes what are called 1,3 diaxial interactions with the other two groups that are axial and on the same side of that cyclohexane ring. Okay, these are called 1,3 diaxial interactions. Those are relative numbers. So if the carbon with my methyl group is carbon 1, then at relative position carbon 3, I see another axial position that's above the plane of the ring. So these 1,3 diaxial interactions then destabilize the molecule, and they're simply steric interactions. Remember, a methyl group is just a cloud of electron density. And so you can kind of get a better picture over here for the fact that there's starting to be some closeness in space of the methyl group and these two hydrogens. And if we draw a space-filling model of this, you can see that those two sets of groups are really close together in space. So it turns out that having a group axial causes 1,3 diaxial interactions, and having it equatorial, there's no 1,3 diaxial interaction. So here's the methyl group being equatorial. So in this case, there's no diaxial interactions, but there are diaxial interactions when it's axial, and so therefore this is going to be the less stable position or less stable conformation, whereas putting it equatorial, you're going to have the more stable of the conformations. And the bigger the group, the more unstable it is to put that large group axial. Okay. Now if you do some calculations on this, these two conformations differ by about 1.4 kilocalories per mole in energy. And if we took and treated this as if it was an equilibrium between two compounds, and this energy is the delta G, and we use the equation delta G equals minus RT ln K, and we calculate the K, and we figure out the percentage of molecules on the equatorial and axial side. Okay, it's a lot of calculations. We would find out that 90 to 95% of the molecules are in the equatorial conformation when you have an energy of about 1.4 kilocalories per mole. And as that energy goes up, that means the percentages in the more stable conformation get even larger. Okay, it doesn't take much energy to cause an equilibrium to shift from 50-50 up to 90 to 95%. Okay, so hopefully you see the destabilizing interaction here of the methyl group being axial and the diaxial interactions. And of course, if we've got two alkyl groups that are diaxial to each other, then that's going to be a really, really unstable conformation. Okay. So, kinds of problems that we'll do with cyclohexane conformations is to say this. Let's say I draw out a conformation and I say, let's draw all the possible conformations for cis 1,3 dimethyl cyclohexane. Well, there's going to be two different chair conformations for the cis 1,3 dimethyl cyclohexane. There would be the boat, and there's a whole bunch of other half twists and full twists and triple twists and all sorts of other conformations in there. But really, we're going to deal with the most stable conformation, the chair conformation. So there's two possible chair conformations for cis 1,3 dimethyl cyclohexane. So I like to choose this carbon as carbon 1. And so there's my axial and my equatorial positions. And now I've gotten myself in trouble because I put that too close to the cis, so I'm going to have to erase the cis and put it up here. How about that? So in the 3 position, 1, 2, 3, I'm going to have an axial up and an equatorial, another axial up and an equatorial. When we write these conformations, we could put all the other hydrogens in around the ring, but we're not going to do that. We're going to just focus on carbon 1 and carbon 3. So this is cis 1,3-dimethyl cyclohexane. So I could start the methyl group out, the first methyl group on, let's say that's carbon 1 and this is carbon 3. Let's say I put the methyl group being axial to start with. Now, what I'm going to do is I'm going to do a ring flip, but I'm not going to write the left-handed or right-handed version of this. I'm going to simply say, you know what, the methyl group can be axial or the methyl group can be equatorial. But now here comes the tricky part. The tricky part is that I now have to put the second methyl group in on carbon 3, but I've asked to write cis. So now I have to look at this molecule and I have to say, where would I put the methyl group on carbon 3 to make it cis to the first methyl group? Do you have an answer? Well, my answer would be that I need to put that methyl group in the axial position because the axial position here is above the plane of the ring. The axial position over here on carbon 1 is above the plane of the ring, and so that means both methyl groups are on the same side of the ring. And so this would be one possible conformation of cis 1,3-dimethyl cyclohexane. If I put the first methyl group equatorial, where would the second methyl group have to go on carbon 3 to be cis? If you said that it would have to go in the equatorial position, you're right. Because this methyl group on this axial position is below the plane of the ring, this methyl group is below the plane of the ring, and therefore they're cis. Which of these two conformations is the most stable? The one on the left or the one on the right? If you said the one on the right is more stable, you are correct, because it has the two methyl groups equatorial, and there's no 1,3-diaxial interactions other than the diaxial interactions between the hydrogens, which have to be there. But if I look at the structure on the left, I have 1,3-diaxial interactions between the methyls and the hydrogen, but I also have some 1,3-diaxial interactions between the methyl groups as well. And so those are going to make this conformation to be less stable. Can you do this for trans? Let's write the two possible conformations of trans 1,3 dimethyl cyclohexane. I'm going to use the same approach. Carbon 1, axial equatorial. Carbon 3, axial and equatorial. Let's put the first methyl group axial. Then let's put it equatorial. And again, this would be the equivalent of doing a ring flip, but when I ring flip the molecule, I'm just not showing it in the left and the right-handed, because to start with, it's going to be tough enough just to draw one of these legibly, let alone more than one. Okay, so where would the second methyl group go in the structure to the left to make trans. If you said equatorial, you are correct. Because this methyl group is above the plane of the ring, and so this methyl group must be below the plane of the ring, and in this case, the equatorial position is below the plane of the ring. Over here, where would the second methyl go on carbon 3 to make trans? Would it go axial or would it go equatorial? If you said axial, you're correct. Because now this methyl group is above the plane of the ring, and this methyl group is below the plane of the ring. Which one of these two conformations is more stable? The one on the left or the one on the right? Trick question, because they're the same, they have the same energy. If we look at the conformation on the left, I've got a methyl group with 2,1,3 diaxial interactions with the hydrogen. If I look at the structure on the right, I've got the methyl group having 2,1,3 diaxial interactions as well. So it turns out that these two have the same energy. So now let's do what we did for the non-cyclic alkanes. Can I rank all four of these structures from number 1 to number 4 in terms of stability? If you said that having both methyl groups equatorial was the most stable, yes. If you said having one methyl axial and one methyl equatorial is next most stable, yes. If you said that having both groups axial was the least stable of all four, then you win. Okay. So these are the kinds of problems that we're going to do. We're going to be given a molecule, and I usually give you the cis and the trans. You write the two conformations for cis, two conformations for trans, and then rank them according to energies from number 1 to number 4. Okay. If you think you've got the hang of this, how about we do this for the 1,4 dimethyl cyclohexane? Could you write the two conformations, the two chair conformations for cis, write the two conformations for trans, and then more importantly, can you rank then overall from number 1 most stable to number 4 least stable? Can you do that for the 1,4 dimethyl cyclohexane? Now I think we'll start, if there aren't any questions on Friday in class, with this one. Can you do the same thing with 1,2 dimethyl cyclohexane? Draw two chair conformations for the cis, two chair conformations for the trans, and then more importantly, can you rank the energies from number 1 most stable to number 4 least stable? Okay. So I would say, why don't you try 1,3, try 1,4, try 1,2, because we'll actually start with both of those in class on Friday. And the 1,2 has a little twist to it that may or may not make a difference in the way that you think. So it's not a trick question. There are no trick questions. But does require us to think about something and remember that what we're doing is we're looking at the destabilizing interactions, the 1,3 diaxial interactions. Those are the key ones that we're looking at. Those are the destabilizing interactions that we use to make our judgments about energy. Okay, so this is what we'll do on Friday. And if you have questions, bring them. We'll do the questions before we start. And then otherwise, we'll look at what your answers were for 1.4, 1.2, and I got a whole bag of more problems that we can do on Friday.